Hi, everybody. Today we're going to be working through our properties of logs. Now, this lesson's coming in right after the introduction to logs, so we should be okay to be able to work through and simplify logs and evaluate logs. Today what we want to talk about is the properties of logs. Now, normally we would go through and we would spend time developing those properties of logs. We would spend time proving them. But kind of in this situation, what we're going to do is we're just going to address those properties of logs, and we'll see an example to see how they work. So, for instance, take a look at this first property of logs. Now, I've labeled it A, but there is no hierarchy of laws of logarithms. So, it's an important law, power law, or log law, but it's not like it has this is the first law of logarithms. First one says that if I have the log of xy from base A, then it's equal to log x from base A plus log y from base A. Our first law of logarithms you see in blue. Really what that is, if we break down the notation, is it says that if I have multiplication inside my log, I can break that apart into the addition of two logs. And if we recall from last time, really logs are just powers, but looking at them from a different perspective. That means logs are exponents. Then it shouldn't surprise us that when we see multiplication, we know that we add the exponents. And so notice we can look at this first law of logarithms almost like using our power laws. When I multiply powers of the same base, I add the exponents. So when I see multiply on the inside of my log, I add my logs. Now, take a look in green, and you'll notice that what we have is a quick example. If I was to go through and take log 4 from base 2 plus log 8 from base 2 and evaluate that, I could evaluate both of those logs. The first one saying 2 to what exponent gives me 4, that's 2. The second log saying 2 to what exponent gives me 8, that's 3. And when I simplify that, I get 5. The alternate way to be able to deal with that, just to show that that law of logarithms is true, is I could take my first line and say, I see that I have addition in between my two logs, which means that I could multiply inside my log. So I'm going to take the result of this log and the result of this log, and when I multiply those together, I get my 32. And now I can evaluate that. 2 to what exponent gives me 32, and I come in on 5, and we're good. Again, we haven't proven it, but given the circumstances, that should be at least enough for us to see that that statement's true. If I was to now jump to a second law of logarithms, if we really understood the first one, second one shouldn't be a surprise. When you examine that first one, you notice that you have division inside of your log, and if I divide powers of the same base, that means that I subtract my exponents. And so what that power or that law of logarithm says is if I see division on the inside, I can break it up into subtraction. And so for the same reason we can see in our green example, if I was to evaluate that, the first log, 2 to what exponent gives me 16, that's 4. The second log, 2 to what exponent gives me 4, that's 2. And if I go through and I subtract those, I get 2. Now, alternatively, what we could do is we could use that law of logarithms, and we could say that I see subtraction in between my two logs, and I know that that means that I could write that as division within a log. Since I have the same base, I'm allowed to do that. And so now what I can do is I can evaluate what's on the inside of my log. 16 divided by 4 gives me 4. And now I can evaluate my log. 2 to what exponent gives me 4? 2. Now we jump to that last law of logarithms. And this one's going to look a little different because you notice you don't have two logs. But I think, again, if we relate these back to our power laws, we should be able to kind of tie everything together. Look in blue, You see that you have log m to the exponent n from base a, and you could write that as n log m from base a. When we start to examine that law of logarithms, the biggest thing for us is to denote that if I have a power inside of my log, a single power, then I can write that as one exponent multiplied by my log. I want you to notice this is my power rule. If I have a power raised to another exponent, then I multiply my exponents. My log is an exponent, and so is the exponent n. As we take a peek at that, I think what we're going to tend to do when we view that power law is we're going to start to look at it this way. That if I have a single log inside my exponent, inside my log, I can bring that exponent out in front. And you then see that it is n multiplied by your log. So, as another example again, you take a peek. We've got log 81 from base 3. I can evaluate that right now because 3 to what exponent gives me 81? That would be 4. Or what I could do is I could view that inside as, well, 81 is 3 to the exponent 4. And yes, this becomes my duh log again. But I could also now do this. I see a single power inside my log, so I'm going to bring that exponent out in front. And now when I evaluate that log, 3 to what exponent gives me 3? That's a 1, and we get down to 4. There is a very quick example of our laws of logarithms. We've got 3 of them. We need to know them. So now what I want to do, I want to jump into kind of some scenarios. Now this might seem like a little bit of a weird scenario, but this is going to show us how this can be a little meaningful for us. Question 1 just asks you to write log 15 from base 2 as the sum of 2 logs. We're getting to the point now where I would say, if you're ready to, pause the video and see if you can work your way through each of these problems. So, pause the video, give it a shot, and see how it goes. Okay, we're back. And as we take a look at A, I have to write the sum of 2 logs for that single log, log 15 from base 2. Well, I know that if I have the sum of 2 logs, that means that I must have multiplication on the inside of my log. So, if I was to think of log 15 as log 5 times 3 from base 2, then now I can see that I have multiplication on the inside of my log, and that means that I can write that as the sum of 2 logs. Now, one key thing. I would have some people that are going to look at that and they go like, well, but like the nice thing then is, why don't I just view, sorry for the why don't I just view log 15 as like 15 times 1? Because then I can go through and I can say, well, I've got log 15 from base 2 plus log 1 from base 2. I want you to notice that wouldn't be acceptable. Because look at your second log. Do you notice how you can evaluate that? 2 to what exponent gives you 1? That's 0. And so because we could evaluate it, we wouldn't accept that as a statement. Your red solution is going to be one of your only solutions. Now, I want you to take a look at B. We have to write log 15 from base 2 as the difference of 2 logs. We should be okay to be able to tackle that one. If I'm taking a look at 15, then really what I have is I need to think of 15 as 2 numbers that would divide. My first instinct might be this. And view 15 as 30 divided by 2. That works really well. And now I have division inside my log, which means I can subtract. But you guys can see the problem that we've now faced with that second log. It can be evaluated to a value of 1. Therefore, we would not accept that solution. So what's the best way to maybe think about log 15? Let's think of it as 45 divided by 3. Notice neither 45 nor 3 are powers base 2. And so with that division inside that log, I can now write that as the subtraction of 2 logs. And for each of those logs, I cannot evaluate further. Okay, that just gets us used to using some of our laws of logarithms. We're going to jump one more example with that. I want you to write log 16 from base 5 as a product of a whole number and a log. Now, this one's going to look a little different, and I would expect kind of 2 common responses to this one. If I was to view log 16 as log 4 squared, notice I now have a single power inside of my log. That means I can bring that exponent out in front and write that through multiply. We would then say that 2 was the coefficient on log 4 from base 5. I want you to just notice one important thing. That is not a single log. It's a whole number and a log. However, the confusing part at times is it is a single term. So it is not a single log, however, it is a single term. Now, the alternate solution that I could have had quite a few people, maybe instead look at 16 as that being 2 to the 4th. And then instead, they would have brought an exponent of 4 out in front and given that. Both of those solutions, perfect. Okay, we're going to follow 2 more instructions. There's going to be a lot of times where you're going to be asked to simplify something to a single log. Again, not a single term, but a single log. And so when we take a look at question 3a, 2 log 5 from base 6, we notice that's not a single log. It is a coefficient, a value, multiplied by a log. And so if we need to change that into a single log, just the same as we can move an exponent outside, we could also move a coefficient back inside. And therefore, I could apply that law of logarithms and get to that. Now that is a single log, fully acceptable. However, some other people might say it's actually easier just to work with, instead of 5 squared 25, you could give me either blue solution and you're good. Part B might look a little uglier because now all of a sudden we have variables. However, I think part B is actually pretty straightforward. You have to write log x plus log y plus log z all as a single log. Now we do notice that there was no base written for any of those logs, and so we recognize that those are all base 10. And since they all have the same base, and we see addition in between, we know that we can write that as multiplication on the inside. You could go straight to this. It's x times y times z all inside my log. Now, brackets would not be required in that instance. However, sometimes by putting brackets on that, we can avoid any sort of confusion of, did you mean like log xy then times z, where it was only the xy on the inside? If we put brackets around everything, everybody understands what we're writing. Okay, last case. I want to work my way through C, and we can now go through and address writing that log 4 from base 6 plus log 3 from base 6 plus log 3 from base 6. Now, I am not saying anybody would tackle this problem this way, but I want to show you just an alternate solution to something that you guys should be able to kind of see, but it can really open the window for us as to where we go. I might have an awful lot of people that notice that the last 2 logs that we have there are the exact same thing. I have log 3 from base 6 plus log 3 from base 6. So I have one term plus another term. And if I have something plus something, then I have two of those somethings. And I can collect my logs just as I would collect any term. Now, by no means am I saying that this is a pattern to go through. By no means am I saying that this is efficient. But if I did take that angle, now what's important is for me to get down to a single log plus a single log. We notice that 2 is causing a problem right now. And so I can't be fixated on the addition in between until I can eliminate that 2. And so if I move that 2 back inside, now I have a single log equal to a single log. And since I have addition in between, then I can write that as multiplication on the inside. And I could actually go all the way to the point of evaluating that. Don't. What is the instruction in the problem? Write it as a single log. Then we're going to stop at log 36 from base 6. Okay, last portion for us to go through is to deal with a different instruction. And this is us talking about how do we go through and evaluate our logs. So I want you to take a look at the first one. Log 3 from base 6 plus log 12 from base 6. And the first thing I want you to notice is that you cannot evaluate each of those logs. 6 to what exponent gives me 3? I don't know. That's not something nice and neat. 6 to what exponent gives me 12? Same answer. However, we do notice that what we have is the addition of logs of the same base. And if I'm adding 2 logs of the same base, then I know that I can write that as multiplication on the inside. Now, since my instruction says evaluate, I can take log 36 from base 6 and evaluate that to 2. Nice. You take a look at B, and I want you to notice that B would have been the combination for us of 2 more difficult problems from our introduction day. 4 to what exponent gives me 32, I can evaluate that. And I could go through and say, okay, well, 32 can be written as a power base 2, and so can 4. So if I viewed that as like a 2 squared and 32 as like a 2 to the 5th, then I could evaluate that first log into 5 halves. I could do the same thing on the second log, and if I viewed my 4 as 2 squared, then I can see that I could evaluate that to 1 half. Now that requires me working with fractions, but they're nice neat fractions, and I get 4 halves, and I work my way down to 2. I'd just like you to take a peek at that and just notice that that might not be an efficient way through. So what I'm just going to do is I'm going to get rid of all that blue solution, hopefully. And then, instead of going through and evaluating each of those individual logs, since each one of them isn't an integer answer, I may choose to look at that and say, well, I notice that I have subtraction in between 2 logs of the same base. And I know that if I have subtraction in between, then that means that I can have division on the inside. And if I was to jump straight to my 32 divided by 2, I get down to 16. And if I then evaluated 4 to what exponent gives me 16, I can get to 2. For most of us, we won't even include that line in our solution, and you may find that line to be much more efficient. So if we were to continue on, I want to walk through a couple more problems as we go. So the first one I'd like to go through is part C, which is 2 log 15 from base 4. From base 5 minus log 9 from base 5. We may jump the gun a little bit to evaluate that. and be so focused on the subtraction in between the logs that we skip over the fact that that is not the subtraction of 2 logs, because my first log has a coefficient on it. So for me to go through, I need to deal with that 2 at the very beginning, which means I'm going to move that back inside the log. If I was to then calculate 15 to the exponent 2, that's going to give me a 225. And now that I get to that point, I've kind of cured my problem. Now I have a single log subtract a single log. They both have the same base, which means that I can do division inside my log. When I divide 25 divided by 9, I'm going to get 25. And now when I evaluate log, now I'm kind of making it look like every one of these problems works out to a value of 2. However, just a fluke, just a fluke. Last problem I'd really like to kind of hit up on basic properties would be D. I want you to work your way through log 32 to the exponent 4 from base 2. And we'll see if we match up. Okay, we're going to work our way through this problem, and perhaps, since we've been talking about properties of logs so far, I might have quite a few people that would say, I'm going to bring that 4 out in front right off the bat. I have a single power inside my log, so I can write that as my exponent times my log. Because now that log is relatively easy to evaluate. 2 to what exponent gives me 32 is 5, and I can simplify to 20. I may have had a bunch of people on instinct instead say, yeah, but I can write 32 as 2 to the 5th. And then when I reduce that power on the inside, I have a power raised to another exponent, and you work your way through. That blue solution would have been how we would have dealt with that log last time. Now we have an alternate method to be able to work our way through. Okay, last problem, and this is the one that I want you to use as your gauge. So as you are working through E, I want you to try to go through and evaluate this big, ugly expression. Okay, pause the video, give it a shot, we'll see how we do. Okay, we're back. If I was to work through this problem, the first thing I notice is all those logs have the same base. And so I can start to use properties of logs. Now, I could put the first log together with the last log because they're both single logs. But I think if I were to tackle this problem, I might just want to make all of them single logs. And so I'm going to move that exponent 1/2 back inside. So when I do that, my next line is going to be 8 to the exponent 1/2. I'm going to argue we should be okay if I wanted to write that as a 2 root 2. Because we know it's the square root of 8 reduced. And now what I have is a bunch of single logs. I can use my properties of logs. So I can combine those all into a single log, base 4. I have addition between the first 2 logs, which means that I need to have multiplication between them. And then I have subtraction of my last log, which means I have division. We get down to that point, and I can now simplify what I have on the inside. I have 6 root 2 over 6. My 6's are going to divide out. And now I have a single log ready to evaluate. So if I was to view that, my 4 is really like a 2 squared. My 2 is a 2 to the exponent 1/2. And so 2 squared to what exponent gives me 2 to the exponent 1/2. I have to get rid of the squared and then put an exponent of 1/2. And when I reduce, I get down to 1/4. Okay. Hopefully everything went well today, and we can spend some time just getting used to applying our laws of logarithms. Okay, jump in and play around with the work on your weekly schedule. Hopefully everything goes well. Good luck.